Hey, what's up, everyone? How are y'all today? Doing good myself. Good to hear. Ooh, that's never a good feeling. Ouch. Exam pretty rough. It's like everyone's in the same boat. Exam season. Yeah, I really sucks. There's always a week or two where everyone has their exams. I mean, for obvious reasons, but it really sucks. Dynamics is not it, Chief. All right. Okay.
Professor, will our exam scores be coming out soon? One of my friends had just texted me and said that he got his score back from a different class, but I thought that was kind of fast.
Yeah. So some some instructors, I was busy yesterday. Today's kind of an off day. Today's when I'm going to be grading. Um, but it depends on the instructor. Some people will start grading like the day of. And I wasn't really able to do that. But today I am hopefully going to finish grading. I'm not sure how long it's going to take, but I'm going to try to get it finished up today. If not today, then probably probably tomorrow. But yeah, uh, I will be grading today. But yeah, that is quite fast. Okay. So today we're talking about, whoops, limits and continuity of these functions as several variables. That we looked at yesterday. Okay. So let's quickly remind ourselves how limits work for functions of one variable, and then we'll see how things are a lot more complicated, unfortunately, for functions of several variables. Oh my goodness. So we have a function of single variable, f of x. And let's look at the graph. Suppose it looks something like this. Maybe the function's not defined. At x equals a, suppose. But we can still talk about a limit, even if the function's not defined there. So suppose this is C. So suppose we want to see what the limit as x approaches a of this function f of x. So if we look at this graphically, what's going on here? So the function's not actually defined there. So saying f of a doesn't make sense because f doesn't take on a value at a. But we can talk about the limit. And the way we evaluate the limit is we look at the limit from the left and the limit from the right. So the limit from the left is c in this case. And the limit as x approaches a from the right right, so if you follow the graph of your function as you approach it from the left, we approach c. And if you follow it from the right, we also approach c. So those are the only two ways we can approach a, from the left and from the right. And since the limit from both directions is the same, c, those two agree. The limit from the left and the limit from the right agree. So the limit exists and it's equal to c. So it could happen that the limit from the left and the limit from the right don't agree. So limit as x approaches a from the left of this function does not equal the limit as x approaches a from the right. Oops. So we say the limit as x approaches a of our function does not exist. And I'll be writing D and E a bunch, so that stands for does not exist. And there are a few different ways the limit can fail to exist. You could have a jump discontinuity here. You could have an infinite discontinuity, other stuff, or infinite, yeah. But for functions of one variable, the important thing is we're a function of one variable, so we're looking at what happens to that one variable. So if we look at the real line where x lives, and we approach a, the important thing is there are only two ways to approach it, from the left and from the right. So those are the only two things we have to check. We have to approach a from the left, see what that limit is, approach a from the right, see what that limit is, and if the two things exist and are equal, the limit exists. So things are more complicated by a lot for functions of two variables and so on and so forth, because now instead of just having to approach a point from the left and from the right, we have infinitely many ways to approach a given point. So keep in mind here, this is not the graph of the function. This is just where x and y live. So suppose we have a function of two variables. And we want to look at the limit as we approach a point AB. So remember, we're a function of two variables. We're plugging in a point in the plane into our function, and it's spitting out a number. So if we were actually looking at the graph of this, this would be the surface z equals f of xy, and it would live in R3. But now we're just going to look at where the points that we're plugging into this live. So like this was the real line where the points that we plug into functions of one variable live. This is the plane where the points we plug into functions of two variables live. So we want to approach AB. So the same thing is true. We want to take every possible way we can. So we look at a path that approaches the point AB. So suppose we travel along this path here and approach AB. We'll see how in a sec, we can take the limit along that path. And we'll see how we do that. And we can evaluate that. And then we can take a limit along, say, another path. Or another path. And another path. So there are infinitely many ways we can approach that. And in fact, it's much nastier than it looks. There aren't just infinitely many straight directions. We can approach along different curves. We can do all sorts of ridiculous things. And these could, in theory, yield different limits. So there are infinitely many paths which approach the point we're taking the limit at. And we need to check, well, we don't, we'll see, we don't actually need to, but here's why this is so much more difficult. So there are literally two paths in on the real line where you can approach A, right? So there are only two things you need to check to show that a limit exists for functions of one variable, limit from the left, limit from the right. If they exist and are equal, boom, you got your limit. For functions of two variables, there are infinitely many ways we can approach a point. And in order for this limit to exist, the limit along every single path has to exist and be equal. So in theory, this is not looking great for establishing that limits exist, because so far it looks like we need to check along every single path, which is, I mean, none of us have infinite time to check along every single path. But the kicker here is, this is the important bit. So the limit as xy approaches AB of a function does not exist. So a function of two variables. If you can find two paths which disagree, where the limits are different. So be careful. This is not saying if you check a bunch of different paths and they all give the same limit, that doesn't prove the limit exists, because there could still be some other path out there which gives a different limit, and maybe you just didn't check it. So even if infinitely many paths give the same limit, if all of them don't, every single one, if there's some other path out there which gives a different limit, then the limit does not exist with that function. So let's look at some examples of limits not existing. So basically everything we're going to look at is the limit as we approach 0, 0, just because that's a lot easier to check. When we're showing limits don't exist. Well, we'll see later how to show limits do exist, but yeah, all these examples we're going to use are going to be approaching 0, 0, just because it's a little easier. So let's look at the limit as y approaches 0, 0 of the function x squared over x squared plus y squared. Okay. So we're approaching 0, 0. Keep in mind, this is not the graph of the function. This is just where x and y live. So we want to approach 0, 0. Let's see if we can find two different paths, evaluate the limit along those, which I'll show you how to do, and then see if we get different results. If we get two different limits along two different paths, then the limit does not exist, because the limit along every single path to 0, 0 has to be the same if the limit does exist. So let's approach along the x-axis and along the y-axis. Probably the two simplest paths we could take. Okay, so we're approaching along the x-axis. We want to take the limit. Essentially what we're doing with these when we're taking the limit is we're turning them into functions of one variable, basically, and then taking the limit, because we know how to deal with functions of one variable. Okay, so along the x-axis, what are the form of the points on the x-axis? So just in general, a point is x, y. What's true of all points on the x-axis?
Y is 0.
Y is equal to 0. So everything on the x-axis is of the form x, 0, right? Because y is always equal to 0. So that's what every point on the x-axis looks like. And if we want to approach 0, 0 along the x-axis, we need to take x to 0, right? Because y is already equal to 0. So we're on the x-axis. We want to go to the point 0, 0. Well, we just need to take x to 0, right? Because y is already equal to 0. So what we do is we take those points x, 0, we plug them into our function, and then we take x to 0. So we have x squared over x squared plus 0 squared. Let me do it like this. Let me write it like this. Okay, so now we have the limit as x goes to 0. So we plug in x for x, 0 for y. So we get x squared over x squared plus 0 squared. And what's the limit as x goes to 0 of x squared over x squared plus 0 squared? We get 1, right? Okay, so we took the limit along the x-axis here. Right, points along the x-axis, y is always 0, so the form x0. If we want to go to 0, 0, we take x to 0. So you make that substitution. Notice only x exists now, so it's a function of one variable. We know how to take limits of functions of one variable. So now let's check along the y-axis. So points along the y-axis, x is always equal to 0. So if we want to take points 0, y to 0, 0, we just take y to 0. So we plug in 0 for x, y for y, and we take y to 0, and then we take the limit. So limit as y goes to 0. So our function was x squared over x squared plus y squared. We're plugging in 0 for x and y for y. And what is the limit as y goes to 0 of 0 squared over 0 squared plus y squared? It's 0. So the limit along x-axis is not equal to the limit along y-axis. So we have two different paths to the origin that yield different limits. So the limit does not exist. To show a limit doesn't exist, you need to find two paths to your point which give different limits. If two paths disagree, the limit does not exist. That is how you always show this. Okay. So let's do a slightly different example. So instead of x squared over x squared plus y squared, let's do xy over x squared plus y squared. Okay, so we're approaching 0, 0 again. Let's really, really quickly do what we just did. So let's check along the x-axis and the y-axis. In the future, this is probably not how you're going to do this. I'll actually show you the best way to do this in the future. But we're going to check along the x-axis. Right, so y is 0. Plug in x for x, 0 for y. Take x to 0. When we do that, we get x times 0 over x squared plus 0 squared. We get 0. So we approach along the x-axis, we get 0. And if we go along the y-axis, right, x is 0. So we plug in, the points are the form 0, y, because x is 0. So plug in x equals 0, y equals y, and take y to 0. So we get 0 times y over 0 squared plus y squared. This limit is also 0. So the limit along the x-axis, the limit along the y-axis agree, but that doesn't tell us anything because there are infinitely many other things, ways we could approach 0, 0, which could give a different limit. So this is inconclusive here. But the best way to check here is we can actually check along any straight line to the origin, basically in one go, right? So all straight lines through the origin are going to be of the lines, the equation of the lines are going to be y equals mx. So this is a quick way to prove some limits don't exist. So it's b is going to be 0 in this case because we're approaching the origin. That's why we approach 0, 0 for these, because it's a lot easier to check. But all lines of the form y equals mx are all the straight lines through the origin. Yeah. So along y equals mx, points are the form x, and like we said, y is equal to mx. So these, if you're along these lines, you're of the form x, mx. And if we want to take that to the origin, we take x to 0. And the nice thing about this is you can just leave m unspecified. And if the limit you get at the end depends on the m you plug in, if different m's give you different limits, then you know the limit doesn't exist, right? Because you can say go along y equals x and y equals 2x. If m equals 1 and m equals 2 gives two different limits, then you know the limit doesn't exist. So let's check. Okay, so along y equals mx, we're going to plug x for x, mx for y into our function. And we're going to take x to 0. So like the other ones, we're turning it now into a function of one variable, only involves x, and taking a limit. Be more clear what I'm doing here. So when we do that, so x, y is mx over x squared plus mx quantity squared. So that's the limit as x goes to 0. X times mx is just m times x squared. And x squared plus m squared x squared, we can pull out the x squared. We get x squared times 1 plus m squared. And so you can cancel x squared top and bottom. And we get m over 1 plus m squared. Okay, so since we can let m be anything, and those represent different values of m represent different lines, notice depending on what m I put in here, I'm going to get a different limit, right? If I plug in m equals 0, I get 0 for the limit. If I plug in m equals 1, I get 1/2 for the limit, so on and so forth. But the limit depends on m. So the limit does not exist, right? There are two paths, just pick two different values of m, which give different limits, so the limit does not exist. Any questions about checking limits along y equals mx? Because that is in general how you're going to be checking that limits do not exist. Right, it's because m can be anything, right? I can set m equal to 0, and that would be along the line y equals 0, which would just be the x-axis. Or I could check m equals 1, that'd be along the line y equals x. And if I plug in different values of m, I get different limits, right? If m shows up anywhere in your limit and you can't cancel it, that means your limit depends on m.
So
Plug in different slopes, you get different slopes and you giving you different limits, so then the limit does not exist.
So if the m in the numerator was a 0, would the limit be 0 then? If you still had the 1 plus m squared in the denominator?
Right, so then if you plug in m equals 0, you get 0 for the limit, but if you plug in m equals 1, then you get 1/2. Right, so those are two different paths along two different lines, which give different limits.
Dude, I remember the first party we worked, and I was like drinking the whole time. I was like dead sober though. Like I was drinking, but I didn't feel anything. I come down in the basement and Graham just started ripping me and doing. He goes, "I know Nick was fucking hammered."
I
was
was
like,
to turn off their mic there.
That's sober pledging.
Bro,
sucks,
you gotta
dude.
do-
How do I find out who?
We should ban that.
Your mic's on, bro.
Ban that, dude. I mean, pledges aren't human, but like,
How do I find out whose mic
they should at
this
least be able
is?
to drink.
Hang on.
I
Oh,
think you can mute him.
There we go. Wow.
Oh yeah, that was funny as well.
yo,
I was
Nicholas.
sick as fuck that week. That was the week I got mono.
Okay, hang on. Sorry, guys.
Yo, Nicholas. Your mic's on.
Oh fuck.
That is embarrassing. Hang on. So can y'all just see my big freaking face right now, or can y'all see my whiteboard? Because I see my face and I don't know how to change this. You can see the whiteboard? Excellent. Okay. All right. So everyone understands how to do this.
I actually have one quick question.
Yes.
So, like, I know how you're saying, like, M could be anything, but
Mhm.
isn't, like, normal limit laws, like, you could, like, kind of take the highest, like, you could compare the degrees of M. So couldn't it be, like, if you compared, like, M and M squared, you could say that it's 0, like, and that's the only value, or?
Oh, no, no, no. So, okay, that is, I see where you're confused. We're not taking M to 0. M is a constant, right? And so M is, M could be anything, right? So this is not, we're not taking a limit of this here. So you're thinking of like the limit as x approaches 0 of 0 over 1 plus x squared. That would indeed be 0, but this is the limit, like this is the limit when we plug in y equals mx and x equals x, and we're taking x to 0. And so we can cancel x squared top and bottom. The limit is m over 1 plus m squared, but m is just some constant, right? It can be whatever we want. We're not taking m to 0 or anything. Does that make sense? So like if I check along y equals 1 times x, then I would plug in m equals 1, and I would get the limit is 1/2. If I check along y equals 2x, then that would be m equals 2, and the limit would be 2 over 5. Does that
Yeah, that makes
clear
sense.
up the confusion? Yeah. So it's important that you understand how to do that. Unfortunately, let me do a quick example which shows that even that's not enough to show a limit doesn't exist sometimes. So suppose we had the limit as xy approaches 0, 0 of x squared y over x cubed plus, no, hang on. No. That's not what I wanted. Sorry, let's say x squared plus oh, hang on. I'm being extremely stupid right now. X to, sorry. X to the 4 plus y squared. That's what I want. Yes, sorry, I'm being, yeah. Yep. Okay. So if we check along y equals mx, so what we're trying to do is we're trying to show this limit does not exist. All right, so we want to find two different paths which give different limits. So let's check along y equals mx, which is nice because you can check along infinitely many paths, all the straight lines all at once. So when we do that, we plug in x for x, y, mx for y, and take x to 0. And so we get x squared times mx quantity squared over x to the 4 no, not mx squared, just mx, right? Y is mx over x to the 4 plus mx quantity squared. And so we get limit as x goes to 0 of m times x cubed over x to the 4 plus m squared x squared. And so we can factor the bottom. Let me do that. We can pull out an x squared. And we get x squared plus m. And we can cancel an x squared top and bottom. So we get mx over x squared plus m. And what is this limit as we take x to 0? Well, the top goes to 0, the bottom goes to m. And from our limit rules, which we'll talk about in a second, we get the limit is 0. No matter what m is. So this might seem to indicate that the limit exists because we just checked along every single straight line through the origin, infinitely many of them, and we got the same limit. Well, unfortunately, straight lines are not the only way to approach the origin. What if we approach along y equals x squared instead, right? So we approach the origin along a parabolic path. Like this. So points on y equals x squared, x is equal to x, y is equal to x squared, we take x to 0. So when we sub that in, we get limit as x goes to 0, x squared times y is equal to x squared over x to the 4 plus x squared quantity squared. So we get limit as x goes to 0. X squared times x squared is x to the 4 over x to the 4 plus x squared squared is x to the 4. What is this limit? 1/2, right? So when we check along the straight lines, we get 0. When we check along this parabolic path, we get 1/2. Those are different paths, which give different limits. So the limit does not exist. Okay, but this is going to be an unusual case because you have to look at this and be kind of clever to pick this specific path. And in general, we're just going to give you, if we want you to prove the limits don't exist, it's going to be enough to check along y = mx in general. I think there's some old exams where you kind of had to pull this out of nowhere, but checking y = mx is going to be good enough in general to show limits do not exist. Okay, so I spent longer than I wanted to on that, but how do we show limits do exist? Because this seems pretty helpless, right? There's so many ways limits can fail to exist. How do we show limits do exist? Well, obviously we can't check every single path, but what we can do is use continuity. So we say a function of two variables we say it's continuous at a point A, B, if the limit as we approach that point A, B of our function exists, and so the limit has to exist for you to be continuous, and it has to be equal to the value of the function. At that point AB. So you're continuous if the limit exists and it's equal to the value of the function at that point. Okay, so we're going to use continuity to evaluate limits, which seems backwards because the definition of continuity is the limit has to exist, but in order to show something's continuous, you need to prove the limit exists first, which is kind of the whole problem. But we're going to skip that whole bit, and I'm just going to give you a bunch of functions and say these guys are continuous. And once you know all these classes of functions are continuous, if you want to evaluate a limit, I can just say that is continuous. Here's the limit. And since it's continuous, to find the limit, you just plug in whatever point you're approaching, A, B, into your function and evaluate your function there. And then that is going to be the limit. So I'm going to give you a whole bunch of continuous functions and show you how we use continuity to evaluate limits. So polynomials in X and Y are continuous. So polynomial of one variable is just all the terms are just a constant times X to some positive integer power. A polynomial in X and Y is just all the terms are some constant so some constant X to some positive integer power Y times some positive integer value. So for example, this would be a polynomial, right? 3x squared minus 2xy squared plus xy to the fourth. Every term is just a constant times x to some positive integer value times y to some positive integer value. Well, it could be y to the 0, and in the case of the first one. X to the 0 or y to the 0 is just 1. So if x or y doesn't show up in one of the terms, that's fine. But as long as everything in there is raised to a positive integer power, you're good. So these are continuous everywhere. So that's great. You see a polynomial, you know it's continuous. You can evaluate the limit. We'll look at how we do this in a second. Rational functions are continuous. So rational functions are going to be a polynomial divided by a polynomial. So rational functions are continuous where the denominator's not 0. So for example, everything we've looked at so far has been a rational function. Xy over x squared plus y squared is continuous, except where the denominator is 0, which happened to be where we check the limit, which is why the limit did not exist. So rational functions, polynomial divided by a polynomial. And compositions of continuous functions are continuous. So if you have a function of one variable which is continuous, which is basically everything you've dealt with in 140 and 141, and a function of two variables which is continuous, if you compose the two, they're continuous. So for example, e to the negative x squared plus y. So e to the x is a continuous function of one variable, e to the something. And we know g of xy, negative x squared plus y, is also continuous because it's a polynomial. So if we compose the two, if instead of f of x, we take f of, you replace x with g of xy, if you compose the two, it's also continuous. Okay, so if you get something continuous from 140, 141, and then you compose it with something continuous of two variables, then you get a continuous function. Okay, so why is this helpful? Well, suppose we want to take the limit as xy approaches 1, 2 of, let's say, x squared plus 3y squared minus xy over x squared plus y squared. Or whatever. Now let's say, I don't know, 0, 1. How about that? Just to make our lives easier. Okay, so if I give you this limit, a question would typically say, evaluate the limit or show it does not exist. Okay, so the first thing we're going to do is we're going to try to evaluate the limit. So the way we're typically going to do this is we're going to say, okay, is this continuous at 0, 1? So I'll call this my function f of xy, the guy we're taking the limit. Okay, so what type of function is f of xy here? Is it one of the continuous functions I just talked about? Well, it is. It's a rational function. And rational functions are continuous as long as the denominator is not 0. So at the point 0, 1, the denominator is not 0. So it's continuous. So since it's continuous, the definition of continuity says the limit exists and it's equal to the value of the function at the point you're taking the limit. So since I know it's continuous, because I waved my hands and said it's continuous, all I have to do is plug in x equals 0, y equals 1, and that is the limit. So when I do that, I get 0 plus 3 times 1 minus 0 over 0 plus 1. So the limit is 3. Okay, sorry, really quickly. Look at a few, let's do a few limit laws to show how we are going to evaluate more complicated limits. Okay, nah, let's do this. So if each of the limits in the following exists, here are the limit laws. So if we have f of xy plus g of xy, we take the limit of the sum of two functions. If the limit for f and the limit for g exist as we approach a, b, then it's equal to the sum of the limits. In the interest of time, I'm not going to write the limit as xy approaches ab. It'll just be understood. That's what the squiggly lines mean here. So limit of a sum is just the sum of the limits. So if we multiply a function by a constant, so suppose the c is just a constant, then we just get that constant times the limit. So you can pull a constant out of the limit, basically. So if you multiply two functions together and you take the limit, and the limits of both those functions exist, that is just equal to the limit of the first times the limit of the second. And then finally, we have the quotient rule. So we have a function divided by a function. That's just equal to the limit of the top divided by the limit of the bottom. As long as the limit of the bottom is not 0. Oh, sorry. Can I go back for 5 seconds? Sure. We good? Okay, gonna assume yes. I gotta get rolling. So, for example, suppose we look at the limit as xy approaches, let's say 3, 0, of the function x cubed sine y over y. Okay, well, we could use the product law. We could look at the limit as xy approaches 3, 0 of x cubed. That's a polynomial. We know it exists. We know that is continuous there, so we just plug in x equals 3. So we get that limit is 27. And then times the limit as xy approaches 3, 0 of sine y over y. Not continuous, but we know the limit as x approaches 0 of sine x over x is 0. And this is essentially the same thing, except it's y. X doesn't show up, but it's approaching 0. And we know the limit as y approaches 0 of sine y over y is just 1. And so we know both those limits exist. So we know if we multiply the two together, the limit is the product of the limits. And so we get 27. Okay, sorry, I went way over here. My apologies. Any questions about anything today? Okay, since I'm just going to summarize this because this is important. So these evaluate the limit or show they don't exist problems, you're going to do them like this. So the limit as xy approaches AB of a function f of xy. So one is we're going to check continuity. So if f is continuous at the point we're taking the limit at, the limit exists, and it's just equal to f at the point AB. So if we know it's continuous there, we just plug it in. That's the limit. It exists. So it could possibly be not continuous. But we can cancel the 0 in the denominator, which makes it not continuous. Then cancel, take limit. And let me show an example. Or let me explain. If you're left with a continuous thing, then you do it. So if you have like f times g over f. And if f at the point is 0, but you can cancel that top and bottom, and you're left with a continuous thing g, then you take the limit as g approaches AB, or g approaches AB. If you're left with a continuous thing after the cancellation, then you just treat it like number 1. So if neither of those work, we're going to assume the limit does not exist. And we're going to prove it doesn't exist by finding 2 different paths which disagree. So you're going to want to check along. Straight lines to find different limits along different paths. My God, I have gone way over. I am so sorry, you guys. So if it's not continuous, or if we can't cancel the discontinuity, cancel the 0 top and bottom by factoring, and then being left with a continuous thing. If we can't do either of those things, we're going to assume it's not. The limit doesn't exist. And to prove that, we're going to check along y equals mx. And that'll be sufficient for almost every problem. Okay, very sorry. Any questions? Okay, so I am going to go over to the office hour Zoom. And have a great day, guys. I will try to get as much grading as I can done today, and hopefully I can finish. And I'll see you guys tomorrow.